Here we want to put a few things together to figure out how to find the absolute maximum, absolute minimum values of a function. And so this theorem, called the extreme value theorem, meaning it's going to help me figure out the extreme values of my function, says that if we have a continuous function over a closed interval, so we have limited ourselves a little bit. We're only looking right now over a closed interval and bounded. Then there is a point AB at which f has an absolute maximum, and there's a point where it has an absolute minimum. So we know they exist. If I have a continuous function on a closed interval, it's saying no matter what you do, no matter how you try to draw this thing from A to B, if it's continuous, then it's going to have an absolute max and min. So here's an example. You got to draw a nice continuous graph. You can see that the absolute maximum is occurring somewhere in between A and B at a critical point, at one of these high points. And the minimum is occurring at the end point. And that turns out to be the only way things can happen. You can either have a max or a min at an end point, an absolute max or a min. Those are allowed at the end points. Or you can have it somewhere on the interior at one of the critical points. And so that's how we have to try to find that max and min. And that's what this little set of steps says. All you have to do to try to find the max or a min on a closed interval for a continuous function is you evaluate the function at the endpoints. That's going to give you 2 y coordinates. Then you find all your critical points, going through that process of taking a derivative, set it to 0, figure out where it does not exist. And however many you find, you evaluate your function at those. So maybe you got 2 or 3 of those. Let's just say we had a couple. So I found a C1 and a C2. I evaluate my function, not the derivative, but my function at those 2 points. Now I've got 4 y coordinates. Well, it turns out that's the only 4 places you could possibly have a maximum or minimum. That's what this theorem is giving us and the Fermat's theorem together. And so all I have to do is compare all my y coordinates that I just came up with, these 2 and these 2. The largest of these has to be the absolute maximum, and the smallest of these has to be the absolute minimum. The other ones, if there are these other values, well, this one ended up being neither. I didn't draw this to where it had another one, but let's say it did that. That's still continuous. Well, you can see here's a point that I would have a local max or a min. It wouldn't be an absolute, but this one's still the absolute. So one of them, something on the interior, can only be an absolute max or a min if it happens to be a place where it's a critical point. So let's go through the process for this function. It says find the absolute extrema. So step 1, evaluate your function at the endpoint. So I'm just going to make a little table here. I'm going to put my values. I'm just going to say x equal a for just in general, x equals some number. First one is the endpoints. I'm going to plug in the endpoints of -1/2 and 4. So these are the endpoints. Sorry, kind of crammed it in there, but it's abbreviated, endpoints. And so I'm going to then calculate my function at those endpoints. Well, that means plug it back in. I'm going to get -1/2 cubed, which is -1/8. -1/2 squared is 1/4, so I get a -3/4. If you work that out and add 1, not that much work, but I'm going to just start skipping that step. This is going to be 3/4 plus 1. Well, if they all have a common denominator of 8, you got a -1. Double that one, it gives you -6 plus 8, and that's all over 8. And so it looks like I get my +1/8. So that goes here. So that's one of my y coordinates in my list. Putting 4 in, evaluating that one, I'm going to leave that up to you to double check me on this, but if I plug it in, I'm going to get 17. All right, that was my 2 endpoints. Now I got to find the critical points. So that's what's going to come next. Any critical points are going to go here. And so remember, to find the critical points, I take the derivative, which in this case is going to be 3x squared minus 6x. Factor it completely. Factor out at 3x. And what I'm left with is x minus 2. And so I can see, making a little table here, I've got critical points where f is 0 and where f does not exist. That's where I get critical points. Well, the function is 0 when x is 0 or 2. And this function will always exist. This derivative will always exist. There's no denominator. There's nothing to worry about here. that might make that function undefined. So this always exists. So I get two more that are, you got to make sure they're in this interval, and they are. Both of them are 0 and 2. These are the two critical points that I came up with. I plug those back into my original function. 0 is easy enough. You can see that that's 1. 2 is not so bad. It's going to be 8 minus 12. That's a negative 4 plus 1. That's going to be 3. So I've got, it's negative 3, sorry. 8 minus 12 plus 1. So I've got my values, and now I'm just going to ask. This is all just about the absolute extrema. We're not doing the local extrema yet. I just figure out which of these is the absolute max and which is the absolute min. If there is an absolute max or a min, they have to occur at the endpoint or at a critical point. And there are absolute max and min because it's a continuous function on a closed interval. So in this case, the smallest value I get is here. So this is an absolute minimum. It occurs when x is 2, and that is the minimum value. You will not get a smaller value from this graph than negative 3. What about the absolute maximum? That occurs at that endpoint. The absolute maximum occurs at 4, and the maximum value is 17. So if I were to try to sketch this, just a rough sketch, got a negative 1, well, I'm going to say negative 1 here. Got to go all the way out to 4, so I don't want to get too big. 2, 1, 2, 3, and 4. On this other axis, I'm going to have to measure these in 4s, I guess. 4, 8, 12, and 16. So negative 1/2, 1/8 is pretty close to 0 here. And then that's my endpoint. And then from there, I'll go 4 to 17. So that's way up here. That's my two endpoints. And then in the interior, I have 0, 1, which would be somewhere about there. And then 2 minus 3. Go over 2 and down minus 3, so somewhere about there. That's minus 4. And so I connect these dots, something like this. Don't know any other, I mean, there's no other critical points, meaning there's no other places where I'd have a possible horizontal tangent, because that's what we checked for those when we did this derivative and set it equal to 0. So there's not any other horizontal tangents. And so this would have to be a rough sketch of the graph, and you can see that I have a minimum occurring here at negative 3 and a maximum occurring there. And I did plot the graph, so take a quick look at that one again. You can see I've got the rough shape of that graph. Found the max and min. Max at the endpoint, absolute max, and then the minimum kind of here in the middle. Okay, let's do another one that involves some trig functions. So I want to find the absolute extrema on a closed interval. The process is to build this table. You find your critical, we're going to use our endpoints, and then we'll use our critical points. Well, the endpoints are given to us, so I'm going to plug in 0 and 2 pi. That's these two endpoints. And then we'll need the critical points. Well, plugging in 0, I get 0 and minus 2 times sine of 0, which is 0. So I get 0. Plugging in 2 pi, I get 2 pi, and sine of 2 pi is 0. So again, I get, well, not again, but I get 2 pi minus 0. So there's my values at the endpoints. I need my critical points. So I'm going to take my function, take its derivative. Gives me 1 minus 2 sine x. And I know what I need is I need where this derivative is 0 and where the derivative does not exist. Looking at this function, I know it exists. So it's just a matter of figuring out where this is 0. So if I set that equal to 0, I'm going to get, bring the 1 over and divide by negative 2. I'm going to get sine x, cosine x. Took my derivative wrong. That'll mess everything up, so be careful there. I'll get cosine x equal 1/2. And so we've got to figure out where that happens in the interval 0 to 2 pi. Well, you got to remember, cosine is positive in quadrant 1. So I'm looking for an x in quadrant 1, where cosine is positive, and also in quadrant 4. That's where cosine is positive. So an angle in this quadrant and an angle in this quadrant between 0 and 2 pi. Well, let's get the one in quadrant 1, and then we can figure out the one from quadrant 4. Cosine, we can build this triangle. If you don't remember when cosine is 1/2, if this is my angle x, cosine is adjacent over hypotenuse in that triangle. This third side then, using the Pythagorean theorem, would be square root of 3. And hopefully you can recognize that that means cosine is 60 degrees, or for us in radians, pi over 3. So x equal pi over 3. And then we put that in quadrant 4. Well, we have to go all the way around to where it makes an angle with the x-axis of pi over 3. If that's pi over 3, all the way around would be 6 pi over 3. Come back pi over 3 would give you 5 pi over 3. So that would be your other one, 5 pi over 3. So those are my critical points, pi over 3, 5 pi over 3. That's all I get. I don't get any places where the derivative doesn't exist. And then I got to plug these in. Well, again, I'll save you a little bit of time watching me plug them in, because this will give me pi over 3 minus, when I plug it in, sine of pi over 3 is going to be square root of 3 over 2. So I'm going to have 2 times the square root of 3 over 2. And then I plug in 5 pi over 3, and I get 5 pi over 3 minus 2 times, and again it's square root of 3 over 2 because it's sine of that. And I have to pick out which of these is the biggest and which is the smallest. Obviously 0, this is approximately 6.28. Need a calculator for this one. That ends up being approximately, it's negative 0.7, we'll say, because I don't have much room. And then this other one is approximately 6.9. Actually, it's closer to 7, so we'll just say it's 7. So looking at those values, this one's the biggest, and this one's the smallest. So those two critical points are where I have my high and low point in this particular problem. So this is where my absolute min is going to occur, and this is where my absolute max will occur. And here's the graph of this one. Let me make it come on down here. And you can see I ended up with a minimum, not at an endpoint, but here at pi over 3, which is close to 1, because 3.14 over 3 is close to 1. And then over here, turns out I have a maximum of 5 pi over 3, which is close to 5, a little bit bigger than 5, because it's 3.14 over 3 times 5. So those max and mins, those absolute max and mins, can occur at an endpoint, or they can occur at one of those interior points at a critical point. But this process will walk us through the steps you need to do. Get your endpoints, see how big they are and how small. Get your critical points, plug those in, pick your biggest, pick your smallest.